The two circles are tangent at point A. Is BC parallel to DE? Let the center of the smaller circle be F and the center of the larger circle be G. And let's draw a line between the centers that's perpendicular to the line of tangency between the circles. Angles BAF and DAG are vertical angles, so they're congruent. Segments AF and BF are radii of the smaller circle, so let their lengths be R1. When we draw this line through point F and perpendicular to AB, it's tempting to say that it bisects AB, but let's prove it just to be sure. Let's draw this diagram illustrating the problem. We'll label the radii R and draw the perpendicular line through the center, creating two right triangles. The radii are clearly congruent to each other, and the two triangles share the perpendicular line. From there, we can invoke the RHS postulate for right triangle congruence, which states that two right triangles are congruent if their hypotenuses and one of their sides are congruent. That means angles FAB and FBA are congruent, and although we don't know angle AFB, we'll label it just to keep track of for later. The same reasoning applies to triangle ADG. Drawing the perpendicular bisector forms two congruent right triangles, which shows that all three angles of triangle ADG are congruent to those of triangle ABF. This means that triangles ABF and ADG are similar, which we'll show by labeling the remaining sides as a constant multiple of the respective radii. All of the reasoning we used on triangles ABF and ADG also applies to triangles ACF and AEG. The triangles share three congruent angles and are thus similar. So let's let the length of AC be y times r1 and the length of AE be y times r2. Looking back at triangles ABC and ADE, we can see that they each have two sides which differ in length by the same scale factor, with a congruent included angle. This means that triangles ABC and ADE have SAS similarity. Finally, this means that angles ABC and ADE are congruent, which means that BC and DE are parallel.